a mass transfer. So the transfer of the oxygen into the liquid phase is kind of an important part of the process of getting oxygen to the bacteria. So in fact, the E. coli that we're going to use is a facultative aerobe, and therefore it'll live just fine if you forget to increase the oxygen concentration. It'll go anaerobic on you, and it'll be happy. But the problem is that the process will produce some byproducts, and those byproducts will kill the bug. It can only grow at a certain concentration under those conditions. So we are going to try to avoid oxygen limitation, and we will talk about how we go about doing that. So this is a picture. You understand this concept. Oxygen has a very low concentration in water, and in fact, the concentration in the water is sufficient for the bacteria to grow, even to a very high cell density. The concentration is not the issue as much as the rate of transfer of the oxygen from the gas bubble to the liquid. And this just shows you the concentration. This is temperature. Now, what do you see here? The temperature is going up, and the milligrams of oxygen per liter is going down. Okay, so that means at lower temperatures, oxygen has more solubility in the water. Okay, that's an important thing to remember. And you remember this, if we have a bubble of gas and we have an interface and the liquid, that the concentration of oxygen in the bubble is much higher than what actually is in the liquid phase. And so we have the oxygen is going to prefer to be in the gas phase, but we can get it in the liquid phase, and it will reach the saturation concentration, which we saw the values on the previous slide. And so what we are going to need to do is to manage the oxygen transfer. So how do we do that? The oxygen concentrations are going to vary in the bioreactor. And so how do we do this? First of all, let's think of oxygen transfer rate. And we are going to give it a mass transfer coefficient. This is a volumetric mass transfer coefficient, KLA. And this is going to be the concentration of oxygen that is at saturation under those conditions, and under that temperature and in that particular buffer, although we can assume that for all practical purposes that it's in water because it doesn't change that much with the salt. It does change, but not enough to make a big difference. But okay, one thing that does affect this is the presence of surfactants. So that's something to know. Okay, this is the concentration in the liquid phase. So this is actually what we measure. The CL is what we measure with the DO probe. So this is the value that we're going to measure. This KLA, and we will see how are we going to increase the rate of oxygen transfer. Okay. We can either increase the rate of oxygen transfer by increasing KLA, increasing the mass transfer coefficient. Okay? And how do we increase the mass transfer coefficient? Well, one way is to increase the surface area. How do we increase the surface area? That would be by having smaller bubbles. How do we get smaller bubbles? By stirring harder. So we can stir harder, and we get smaller bubbles, and we get more surface area, and we get faster oxygen transfer. We can also change the concentration of oxygen at saturation. And we don't do this in this lab, but you could feed enriched oxygen, or enriched air. So you mix oxygen and air and feed that, and that will increase the concentration of oxygen in the liquid. Okay, so what we're going to talk about here is the need to match the amount of oxygen that the bacteria are consuming. Okay, so here we go. In the beginning of the run, you start with a bioreactor that's saturated with air. And as the bugs grow, they begin to use the oxygen. And if you don't start stirring faster or blowing more air, then your dissolved oxygen concentration will just drop right down to zero, and it will stay at zero. Now, if you're actually stirring in air and feeding in air by blowing air into the system, it doesn't actually mean that the bugs are not getting any oxygen under this condition. It means that they're consuming everything as fast as you put it in. So the probe is not measuring any oxygen. And when you see this happen, this is a bad sign. This is death, unless you're stirring faster. If you start stirring faster, then you'd expect this to go up. If you just leave the system alone and it just goes up on its own, that means the bugs aren't breathing anymore, and that's the end. Okay. So how can we increase the oxygen supply? By stirring faster, or by, okay, let's see, what did I put on this slide? Oxygen, OUR is a rate. All right, so OTR is the transfer rate. Okay, how much are we transferring is one thing, and how much is being consumed is the other. So if we are feeding it and it's being consumed as fast as it's fed, then we are meeting the demand for oxygen. And that's a fine situation. If we reach the point where the oxygen becomes limited, okay, that shows in our reactor by the picture on the previous slide where it's flat at 0. Okay, so we are feeding, and the measurement is 0. Okay, that tells us that the oxygen supply is meeting the demand. Okay, so we can actually meet the demand of our cells by not having oxygen be the limiting nutrient, in which case we will expect to see some residual oxygen in the bioreactor, and that will be determined by seeing a value on the probe other than 0. So we are going to see how to manage. I threw in this little point here that even if the cells are not growing, they still need oxygen. And this is called the maintenance requirement. That one is very small. So when you're at a steady state, you'll see that there is still some oxygen when you reach the state of resting cells. Okay, they're there, they're alive, they're still going to consume some oxygen, but they're not going to consume very much. Okay. So we increase the supply by increasing the transfer rate, and I've already actually explained this. We can either increase the KLA or increase the C-star, and we can increase KLA. Interestingly, this volumetric mass transfer coefficient is directly related to the power input per volume of broth. So this is a correlation that can be used. This is the superficial gas velocity, and you could determine that because if you know the inner diameter of the bioreactor and you know the sparge rate and assume it's a well